So in this lecture, we will continue the discussion of different applications of microfluidic technology and in different areas. So here is the list that we have seen, or some of the applications that we have listed for microfluidics. By no means this list is exhaustive. Actually, while preparing for this lecture, as I look upon the applications of microfluidics, I get to see more and more applications, and then I realize that if I would like to give a comprehensive overview of the fields that microfluidics can have an impact upon, probably I would need another course to discuss the application, all the applications of microfluidics, if I will be able to compile all the applications in one lecture. That will be a humongous task in itself. Okay. So let us look at some more applications, and in this we will look at the some applications in aerospace industry. So in the aerospace industry, there can be different applications of microfluidics. One of them is in flow control of aerodynamic flow control of the aerospace vehicles. These aerospace vehicles can be aeronautical applications, for example aeroplanes, etc., or it can be for space applications for rockets. So these involve sensors, actuators, or thrusting devices, and these applications are generally based on MEMS. MEMS, as you would know, that micro electromechanical systems. So the mechanical and electronic systems which are working at the micron size, they are called MEMS. And so some of those devices are, say, synthetic jet for thrust vectoring. So here is a image of synthetic jet, or it can be supersonic microjets, oscillator, fluidic oscillators, or turbulent boundary layer control. So where these different jets or oscillators, they can affect the overall flow and change the thrust vectoring for over the aerofoils, etc. Another application is in micropropulsion devices. So with the application of satellite in a number of areas, there have been a thrust towards developing smaller and smaller satellites. So based on that, the different names for satellites have also been standardized. A satellite which weighs about 100 kg is named as microsatellite. A satellite which is about 10 kg is a nanosatellite. Picosatellite is 1 kg, and femtosecond satellite is less than 100 grams. This classification I have taken from the microfluidics and nanofluidics handbook. And these satellites, they will have the MEMS based thrusters, and these thrusters based on maybe cold gas thruster or plasma thruster or combustion based thrusters. Now one of the challenges in this is that the impulse bit size, or the small amount of impulse that is required to control these small satellites, so it is very important to have that one can, or one should be able to produce the amount of impulse accurately, so that the accurate or the desired control direction can be given to the satellite. So the kind of impulse, the kind of numbers that are required, you can see from here that for 1 kg mass, the impulse required is about 10 to the power minus 4 to 10 to the power minus 6 newtons second. This requires that one should be able to have the smallest bit of impulse, so that one can have increments over it, but if the minimum amount of impulse is required, that can be given. That is the impulse bit size discussed here. So, that is a typical micro thruster or a schematic of a micro thruster, where there is a propellant and a heater element attached to it. This micro thruster is only few mm in diameter, and the exit diameter of the nozzle, which can be a supersonic nozzle or subsonic nozzle, it's about 250 to 400 microns. And as when this thruster is to be used, the element is heated, and the propellant converts into gas, the pressure builds up, and this diaphragm ruptures, and the gases come out, and the desired thrust is given. Another application in aerospace industry is in micro power generators in terms of, for example, fuel cells and micro turbines. So, these generators are expected to provide power in the range of 1 to 15 watt, and this power might be required for miniature cameras or mobile applications and other applications where power is required. So, among the different fuel cells, direct methanol fuel cell is the preferred method. Here is a schematic of the direct methanol fuel cell, and this image is again taken from handbook of micro and nanofluidics. Okay. So, these direct methanol fuel cells, they have very high energy density of about 5960 watt hour per kg. In these, whatever we have learnt in this course, the gas liquid flow in microchannels. So, some of this work in microchannels have been motivated by the fluid handling and thermal management challenges in PEMF fuel cell or direct methanol fuel cell. So, these are the two biggest challenges in these fuel cells. So, in the aerospace industry, we looked at three applications here. The aerodynamic flow control of aerospace devices, so as to control the lift and drag on the vehicles, and then micro thrusters for micro propulsion devices or for micro satellites, then micro power generators, for example, fuel cells and micro turbines. Okay. Now, coming to chemical process industries, which is the main area of this course, because this course has been offered under the chemical engineering discipline. Because this is a multi-phase flow course, so what I have listed here is some of the gas liquid reactions, and in this image what you see is some of the micro reactors for gas liquid applications. The first one is falling film microreactor, where the liquid film falls on the wall of the channel and the gas comes between the two plates and the interface between the two gas and liquid provide the contact area for the mass transfer between the gas and liquid phases. Another application is micro bubble column. You can guess or estimate the size of the channel by looking at the matchstick. So, the size of the channel window here, what we see here is smaller than a matchstick. The another one is a packed bed reactor. So, where there are different channels and in which it has been packed. So, these are different type of contactors, and I have just listed or shown three contactors here. So, one of the most investigated reaction in microchannels has been halogenation and in particular fluorination. So, this is for example fluorination of toluene. Because this has wide applications in a number of industries, pharmaceuticals, dyes, liquid crystals, crop protection agents. Actually, every third drug contains fluorine moiety. In general, the synthesis route of these fluorine compounds are complex synthetic route. There is no direct synthesis route, and these results in the selectivity of these routes is low, and the amount of material that is wasted is quite high. So, the direct route, it might be cheaper, but it requires precise temperature control because reactions are fast and exothermic, and if the overheating or the hot spot formation happens, then the undesired reaction may take place and one will again get poor selectivity. So, as these fluorine, as we know, that is a very reactive compound. So, the fluorination reactions are very fast, and so they are often limited by the mass transfer between the gas and liquid phases. So, one will need high interfacial area density, which is what we can easily get in microchannels. So, it becomes a good candidate to perform gas liquid reactions in microchannels. One also need, because it is exothermic reaction, so one need to have good heat transfer and try to maintain the isothermal conditions in the reactor, which is very difficult in a large reactor, but it can, or a state tank reactor for example, but it can be done in microchannels. One also need to have precise control over the things, precise control over the residence time, precise control over the pressure and temperature over which the reactor will be operating, because the residence time need to be precise, because if it is too long, then secondary reaction may take place and the selectivity will again be poor. So, by selectivity I mean the yield of the desired product or divided by the yield of the undesired product, which is what we term generally as selectivity in chemical reaction engineering. Another gas liquid reaction which has been studied is carbon-carbon multiple bond addition, for example cycloalkene hydrogenation. So, here is an example of this. This reaction has been performed in trickle bed reactor and it is well studied. So, actually this reaction has been used as benchmarking for micro reactors. It is again a fast reaction and exothermic. So, it can be performed in micro reactions so that hot spots do not form and large interfacial area is provided for the reaction to happen. There are a number of other reactions that have been performed in micro reactors. Now, one of the applications of chemical microprocessing is in the pharmaceutical industry, where in general the trend is to have batch reactor. So, what I mean by batch reactor, that the two reactants or all the reactants are mixed in a vessel or in the reactor, and then the reaction happens. After the reaction, the product is taken out, and then again the vessel is cleaned and it can be used for another reaction, or if the same reaction is to be carried out or same product is to be manufactured, then this without cleaning one can have the reactions. Now, when one does this, then it is highly likely that the product quality from one batch to another batch may differ. So, there might be a non-uniformity in the product. But the use of batch reactors in pharmaceutical industry is preferred because of the low quality or not low quality, but the low quantity of the reactants and products that are involved. One do not need very large scale reactors in pharmaceutical industry, and the chemicals that are dealt with, they are generally of high cost, so they need to be used judiciously to reduce the production cost. Moreover, the same reactor after cleaning can be used for another reaction. So these problems can be circumvented or can be addressed by using continuous microreactors. Microreactors will of course offer the advantage of the continuous flow reactors at the larger scale, but at the same time it will also give one the freedom to perform reactions with low volume of fluids. So one can have this, and then one can number up the process by, or one can scale up the process by having number of microchannel or microreactors in parallel, so that the reaction can be scaled up and it can be performed in the microreactors. So in recent years, in last 2 decades at least, there have been a drive to persuade the pharmaceutical industry looking at the options changing from the batch reactor mode to the continuous flow reactor mode at home as well as internationally. So for example, there has been about 15 or 20 years ago, there has been a Novartis and MIT Center for Continuous Manufacturing, where they looked at different research problems that are required to be addressed for continuous manufacturing of pharmaceutical products. Here are some other news items that there has been investment from Swiss firm Lonza and DS Pharma to convert to microreactor process technology to produce pharmaceutical chemicals. Back home, there is a project running at National Chemical Laboratories, a CSIR lab in Pune, where they have the project is called Indus Magic, in which the goal is to develop novel reactors for process intensification, and one of the reactors that they are looking at actively is microreactors for specialty and fine and specialty chemicals. Mostly these chemicals are used in pharmaceutical industry. So one of the issues that often comes up when one is looking at using microreactors in chemical processing, that how to scale up. So as I have discussed in quite a few times during the course, that this scaling up is achieved by numbering up. So one example is printed circuit heat exchangers, which were developed at the University of Sydney in 1980s, and then it was commercialized by Heatrick, which is now a group of a part of a mega aerospace company. So in these microreactors, on the metal plates, the flow channels are chemically etched, as you can see here, that on a metal plate the channels are etched, and these channels can be straight channel or channels like this, and they can be tortuous passages so as to enhance the mixing. And then these plates are diffusion bonded together, and they will look like this, and then form with the inlet and outlet manifolds. One can create a reactor of this form, which will be very compact reactor. Now this the technology which they use has been used for developing heat exchangers, and it is commercialized successfully. In recent decade, they have been looking at, and Heatrick as well as other companies and researchers have been looking at using the same concept for scaling up the microreactors. So, this is because in this we are not changing the scale of the reactor, rather than the number of the reactors that are being used for the application is being increased. So, for example, in this one can have thousands of microreactors running in parallel. So, one of the problems or one of the challenges in addressing this or in numbering up is that the uniform distribution of the reactant in the channels, because when one have the fluid coming from the manifolds, it is very difficult to distribute the liquid or gas equally in the channels, and this becomes even more challenging when one is dealing with multi-phase flow systems. So, this is an active area of research, that how one can have the equal distribution or the controlled distribution of the fluid in numbered up reactors like this. So, here are two sources of information for the students who want to further know about the chemical microprocessing in so the chemical engineering or reactions in microreactors. One can look at these two volumes by Professor Hassel, Professor Schouten, Rankin, Estrada, and others, Professor Cole, Professor Lowe. So, they are all who have been working on the microreactor technology and its commercialization for last few decades. And this is these books having several volumes are good source of information about the fundamentals of transport processes in microreactors, computational and experimental techniques, as well as the different experimental protocols for different reactions and applications in for reactions in microchannels. Now, let us look at some of the biological applications. By no means the applications that I show cover all the applications, but I just showing few applications. One of this is DNA analysis. So, DNA analysis involves a number of processes and it will be useful for medical diagnostics as well as for point of use testing in agricultural. So, here is a integrated analysis system in which all the steps of the DNA analysis, sample loading, drop metering, thermal reaction, gel loading and electrophoresis, which is for separation of the particles. So, this all have been integrated on a single chip and this such a compact and small scale device can be very useful for analysis of DNA and in these applications. Then another application is encapsulation of the cells, which is required for, say, example drug delivery for treatment of hormone or protein deficient diseases or cancer therapy, for microcarriers or scaffold for cell cultures and tissue engineering. So, this is a system for developing the 300 micron size, the 300 micron size beads which can encapsulate cells. Then there is another application in understanding the hemorheology. So, the hemorheology or the hemodynamics refers to the study of flow of blood, and rheology, as you might know, that rheology is the science of looking at the relationship between stress and rate of strain or the viscosity of the complex fluids. So, as we know that blood is a suspension of red blood cells, white blood cells and platelets in plasma. Now, so it is a complex fluids consisting of plasma which have properties of water, but it also have some proteins associated with it, so which makes it slightly complex, but most of the time it can have the density and viscosity that of water. It has slightly viscoelastic nature, as the recent research has shown. Now, when there are small deformable particles, most of them are red blood cells. So, the suspended particles in the blood, 99% of the suspended particles are red blood cells, and in the total volume of the blood, the volume of these red blood cells will be around 45% in a healthy human being. And this blood which flows in the vascular network, which is the network of arteries, capillaries and veins in the body. Now, the size of the capillaries and smaller arteries, which are called arterioles, and smaller veins, which are called venules, it can be as small as few microns, about 8 to 10 microns. The size of a red blood cells, which is a disc shaped cell, it is about 8 micron in diameter of the disc and 2 micron in thickness. So, as one moves in the smaller veins or smaller arteries or the capillaries, the size of the blood cells and the capillaries are almost same, and the capillaries, when these blood cells are moving through the capillaries, they need to deform and flow through one by one. Even in larger arteries where the diameter is 300 micron or smaller, as you can see here, there is an interesting effect that is observed in capillaries, probably a microchannel effect. This effect is known as Faharius which suggests that the viscosity of the blood, this is relative viscosity of the blood, it decreases when the channel size decreases below 300 mm. So, understanding the processes that is happening at these smaller sizes is very important for number of biomedical applications. For example, the techniques are being developed to estimate the viscosity of blood inside the blood vessels and identify or diagnose the diseases from those. For such application, one need to have very detailed understanding of the fluid mechanics as well as other transport processes that is happening in these micro devices or in these micro channels. So, one need to study first these things in the laboratory environment and gain confidence over it. For example, recently there has been a nano machine developed at Indian Institute of Science in Bangalore, where they plan to measure the viscosity of the blood using a helical coil or nano helical coil using the magnetic field. Another interesting phenomena that happens in or at low shear rates in blood, that the red blood cells, they stack together. So, as you can see here, that at low shear rates, which will often be the case at low velocities and low channel sizes, because the velocities are very high when the blood comes out from the heart, say in aorta and large arteries. When it goes to capillaries, the velocity of the blood will be smaller, so the shear rates will be smaller, and these red blood cells, they tend to aggregate, and this formation is called Rolex formation. And when this formation happens, the viscosity of blood is known to be, or blood is known to be a Newtonian fluid above a certain shear rate. But at lower shear rate, it behaves as a complex fluid. So, it shows the shear thinning behavior. So, all these investigation of the flow of a foreign material in the blood, or flow of red blood cells, their movement, or the movement of sick and healthy red blood cells, all this needs to be investigated in microfluidic devices. So, of course, there is a lot of scope for microfluidics in hemodynamics and hemorrheology. Similarly, it is also the lung is, as we know, that where the exchange of oxygen happens in at a membrane, exchanges of oxygen and carbon dioxide happens between the air and blood, and this happens in a smaller spherical kind of sacs, which are called alveoli. There have been devices which are developed to understand the mass transfer processes that happens at the lung, and then these devices has been named as lung on a chip devices. Okay. Another application which we just saw an example in for DNA analysis is called Micrototal analytical system. So, in analytical chemistry, one need to go through different stages: sample preparation, liquid handling, detection, and reading out the electronics. It will be wonderful if one can combine and integrate all these steps in a single platform, and that is what these micrototal analytical systems are supposed to provide. So, these are also known as micrototal analysis system, or MUTAS, or lab on a chip devices. So, you have all the functions that you need to do in a chemistry lab integrated over a chip. So, that is why the name. And miniaturized analysis system, and they have of course applications anywhere where you want to analyze chemically or biologically a particular sample. So, in medicine, drug discovery, forensic science, biowarfare, defense, environmental monitoring, oil and gas industry, and so on and so forth. So, this is another example of integrated microfluidic cell culture analysis on a chip. We have already seen an example for DNA. Okay, so a related application of this micrototal analysis is has come from Professor Gershenfeld's lab at MIT, where they have suggested that in microfluidics one can use bubble logic. So, one can encode on-chip process control using bubbles for microfluidic devices, where the presence of bubble is 1 and the absence of bubble is 0. So, this bubble is a single bit of information using this 1 and 0, and this bit of information, it can also carry a material or a chemical in these bubbles or droplets. So the computations that happens in these chips can also result in physical material processing at the same time. So one don't need the electronics separately, as they suggest that the microfluidic devices can carry their own process control information without the need for an external microprocessor. So that will be this is just a conceptualization stage, but if it can be done and commercialized, then this will be a wonderful thing, having a lab on a chip device which has its own logic. Okay. So these are some of the applications that we have discussed, and as I said at the start of this lecture, there are a number of applications in a number of walks of in our day-to-day life as well as industry, biomedical applications, aerospace applications, automotive applications, cosmic industry applications, pharmaceutical industry applications, where these microfluidics are required. And as microfluidics depends on the control of the process, one need to have precise control of the systems. Most of the systems that we have discussed are developed in microchannels because they offer the advantage of precise control over the processes. So when one needs the precise control, one need to understand the processes that are happening, and one need to know the fluid mechanics, heat transfer, mass transfer, reactions that are happening in these systems. One also need to, because most of the fluids that we handle are multi-phase flows. So one need to have a very good understanding of the multi-phase microfluidics that happen in these systems. Okay, thank you.